Starting with the complex integral with the definition of an integral as the limit of sum. Let L be any rectifiable arc defined by z equal to zt. Z is depending upon the point t. So this is equal to xt plus iota yt, where t is belonging to the closed interval ab. Let fz be the function of complex variable z, which is defined and continuous on the arc L, the rectifiable arc. So f of z is a function of the complex variable z. Then we consider the partition of closed interval ab as we are taking the initial point to be a, which is represented as t0, and then t1, then t2, up to so on, Tn, which is represented as b. It is the initial point, this is the terminal point. Suppose this is your x and y axis and this is your arc L. The initial point A equal to z0, which is taken to be as z0 depending upon the point t0. This one, z1 is depending on the point t1. Like so on, Zn is depending on the point Tn. So these are the points on the arc L, where xi k is any arbitrary point lying in each of these intervals. From z0 to z1, we take the point to be xi1, let's say. From z1 to z2, it is xi2, up to so on. We can take xi k to be any arbitrary point. We can give any value to this point xi k. Xi k can be taken as zk, or it can also be taken as zk minus 1. It is your arbitrary point. You can take any point to be as xi k. So writing the sum sp to be equal to, we write the format as taking the difference of this interval first, that is z1 minus z0, and because f is the function defined on this arc L, it is your function depending on the complex variable z. So this difference is multiplied with f of, let's say, xi1. If xi k is a point for the interval zk minus 1, if xi k is a point for this interval, let's say xi1 be the point for this interval, xi2 be the point for this interval, right? So when taking the difference of z1, z0, we multiply this with f of xi1, because f is a continuous function defined on this arc L. And here if I take the complex variable zk, then this zk is nothing but, it is the value of zk at the point tk. And because xi k is any arbitrary point, we can represent the point zk to be as xi k. Xi k is an arbitrary point. You can give any value to the xi k. Similarly, the next term will be z2 minus z1 into f of, let's say, xi2, up to so on. If I reach at this interval, then this is zk minus 1 into f of xi k, plus the last one, zn minus 1 into f of xi n. When we sum up all these terms, we are getting this to be in the summation format. The summation zk minus 1 into f of xi k, where k is starting from 1 to n, and where zk is equal to the value of z at the point tk, and xi k is equal to the value of the z at the point alpha k, where this alpha k is belonging to this interval, that is tk minus 1 tk, the closed interval. These are the points on which z is depending. So taking this sum all together, we are getting Sp to be equal to summation k going from 1 to n. For the convenience, I am writing this to be as delta zk. So it is f of xi k into delta zk. Marking this as 2 and this equation to be as 1. So this is the sum of the partition P. Sum of the partition P. If this sum is taken over all possible partitions P, which is tending to the unique limit I, as n tends to infinity, as the number of points are tending to infinity, also simultaneously the mesh of P or the norm of P tends to 0. Then we say that the function f of z is integrable along this arc L, right? Along this arc L, right? Okay. So if the sum Sp taken over all possible partitions P tends to unique limit I as n tends to infinity and as norm P is tending to 0, then we say that fz is integrable from the point A to B along the arc L, and that limit I is equal to the integration of f of z dz along the arc L. So this integral can also be termed as the complex line integral or the line integral of fz along L, or it is definite integral of fz from A to B along L. So thus the integration of fz along L is equal to taking the mesh P tending to 0 and the limit n tends to infinity on the summation k going from 1 to n f of xi k into delta zk or zk minus 1. So this is the definition of the integral as the limit of the sum. Now we are going to evaluate the examples based on this definition. If L is rectifiable arc joining the points z equal to alpha and z equal to beta, this L is the arc which is joining the point z equal to alpha and z equal to beta, which means z0 is alpha and zn is beta. So by using the definition of the integral as the limit of the sum, we need to evaluate this first part. So by definition we know that this is equal to the limit n tends to infinity on the summation k going from 1 to n, because here what is f of xi k? The integrand is 1, right? So this is constant value, that is equal to 1. So writing here 1 and is multiplied with delta zk, that is zk minus 1. When opening this sum we get this is 1 multiplied with this bracket. So when opening the sum we get limit n tends to infinity on this is z1 minus z0 plus when k is 2 we write this to be as z2 minus z1. For k equal to 3 we write z3 minus z2 up to so on. For k equal to n it is zn minus 1. So cancelling all these points will be cancelled out. So remaining point will be limit n tends to infinity. It is zn minus z0. And that is nothing but what is zn? It is beta. This is your zn, this is your z0, the initial point and the final point. It is beta minus alpha. So the value for this integral is beta minus alpha, right? So in particular, if L is closed, if this arc is closed, which means alpha and beta are equal, so in that case this integral will be 0, right? If the arc is closed, the integral is 0. Next, the integration for the mod of dz. So this is equal to the limit n tends to infinity. Now here again the integrand is 1, that is f of xi k is equal to 1 here. So limit n tends to infinity, we write f of xi k is 1, the summation k going from 1 to n f of xi k is 1, so it is multiplied with the mod of dz, that is delta z. So this is zk minus 1. The mod of zk minus 1. So this is equal to, when opening this summation, we get the mod of z1 minus z0 plus the mod of z1 minus z2 plus the mod of z3 minus z2, so on. At the last, the mod of zn minus 1. So this is limit n tending to infinity. What is mod of z1 minus z0? It is your chord. If I join these points by a straight line, we are getting the polygon curve, right? So z1 minus z0 is your chord. And chord of z1 z0 is what? The arc z1 z0, right? So this is the chord z2 z1, so on. We are having the chord zn minus 1. Limit n tending to infinity. The chord z1 z0 is nothing but the arc z1 z0 plus this is the arc z2 z1, so on. And when this n is tending to infinity, for n tending to infinity, we have total this to be the arc length of L. Total sum is the arc length of L, the complete arc length of L, right? Third part, integration for z dz. Now here your f of xi k is xi k, right? Writing z to be as your xi k. Xi k is represented as the value zk, where this xi k is the point on the sub arc joining the points zk minus 1 to zk, right? Since this xi k is arbitrary, this is your arbitrary point, you can give any value to this point. I can set its value to be equal to zk. I can also set its value to be equal to zk minus 1. For one way I set this value to be zk, for the another way I can set this value to be as zk minus 1. It works for both these values. Xk works for both these values. So writing this to be equal to, it is the limit n tends to infinity. F of xi k is xi k. Z is represented as xi k. Please note that xi k is nothing but the value of z at the point alpha k, where this alpha k is belonging to the interval tk minus 1 tk, and tk minus 1 are the points on which z is depending. So it is xi k into zk minus 1. Because xi k is arbitrary, we can set xi k to be equal to zk minus 1 and xi k to be equal to zk. We can set this value to this also and also to this successively. So we are getting this integral to be equal to the limit n tends to infinity. If xi k is equal to zk, then this is zk into zk minus 1. If xi k is equal to zk minus 1, then the same integral will be equal to zk minus 1 into zk minus 1. Adding these two integrals, we are getting 2I to be equal to limit n tends to infinity, the summation k going from 1 to n on zk plus zk minus 1 into zk minus 1. So limit n tends to infinity, the summation k going from 1 to n, applying the formula, it is zk square minus zk minus 1 square. The formula a plus b into a minus b. that is a square minus b square, and when we take the sum on this, we are getting zn whole square minus z naught whole square. Everything will be cancelled out, these two remains. What is zn? It is beta. So beta square minus alpha square. 2i is equal to beta square minus alpha square, or I is equal to beta square minus alpha square divided by 2. This is the answer for this integral. If I solve this integral without the definition for the limit of the sum, we can easily get here the integration for z square divided by 2. Limits, the starting limit is alpha and the ending one is beta. So when putting the limits, the upper limit, it is beta square by 2 minus the lower limit alpha square by 2, that is equal to beta square minus alpha square divided by 2 to be the answer for this integral. And the same answer we are getting by applying the definition for the limit of sum. So this is all about the definition of an integral as a limit of the sum with examples, right? So next time we are going to learn the properties of the complex line integral. Keep watching the contents. Thank you.